Welcome to lesson 10 on power system analysis. In this lesson, we will be continuing from what we did in lesson 9, that is transmission line steady state operation. In lesson 9, we talked about the power flow equations on transmission line under steady state operating conditions. We also discussed how we can compensate for the reactive power flow on the line and thereby maintain the voltage profile on the line. We discussed there static compensation equipment. We also discussed about the rotating compensation equipment. In this lesson, we will talk about the transformer taps and the combination of these equipments. We will also discuss something about the regulating transformers, how we can control the voltage and power flow on the line using these regulating transformers. And after this, we will try to solve some problems which will clarify most of the ideas that we discussed in lesson 9 and what we will be discussing in lesson 10 today. So, we will start with voltage control of a line using tap changing transformers. Here we have this transmission line given by its simple short line model of R plus j x. We have neglected the shunt capacitance for the line in this model, and we have a step up transformer at the sending end. We are assuming that we have a generator on this side and we have a step up transformer here. On this transformer, we have a number of taps on the high voltage side, thereby by changing the taps we change the turns ratio and therefore, the output voltage of the transformer or the voltage of the transformer on the high voltage side. Then on the receiving end, we again have a step down transformer where we have again taps on the high voltage side, and by changing the tap on this side we can get the change in voltage at the load end. Therefore, for any given at the voltage at the supply end, we can, by managing the taps on the two sides of the transmission line, that is on the two transformers on the two sides of the transmission line, we can control the voltage to the load. Now, these taps are what we call as off nominal tap, that is, if it is placed in a position where it is the nominal turns ratio of the transformer. Suppose this is a 11 kV to 220 kV transformer, then when we are putting 11 kV on this side and the low voltage side, and if we put the tap at the nominal position, then we will get 220 kV on the high voltage side. And if we place the tap on the upper side of the nominal tap or on the lower side of the nominal tap, we will get different voltage. If we put it on the upper side, we will get higher voltages. If we put it on the lower side, we will get lower voltages. Normally, the transformers may have taps which can be in terms of variation of plus minus 5 to 10%, with variation at each tap of the order of 2% or 2.5% or so. Similar thing we have on the low voltage side. Here also we can place the taps at the nominal position, then we will get the nominal voltage ratios. If we place the tap above or below, then we will get different voltages. Like if we put it above the nominal position, then the load voltage is going to be somewhat lower than what it will be if it is placed at the nominal position, because high voltage side the turns ratio, number of turns, it will increase, whereas the low voltage side, the number of turns being same, the ratio will get reduced. So, similarly, if we put it on the on the lower side of the nominal, we will get somewhat higher voltage on the low voltage side. Now, normally these taps are always placed on the high voltage winding. One reason is the high voltage winding will be carrying much less current, and therefore, when we are changing this tap, especially if we have on load tap changing transformer, that is OLTC, then the current will be much lower here. Also, it has been found that if we place the taps on the high voltage side, we get a much better voltage control than if we place it on the low voltage side. So, here I am showing in this diagram that we have a voltage T s into V 1 at the sending end, where T s is the off nominal tap ratio. It can be in terms of, say, if it is at 10% above the normal, then the value of T s is 1.1. If it is, say, at 5% below the nominal, then the value of T s will be 0.95. Similarly, on the receiving end side, we have the off nominal tap ratio as T r, and therefore, the voltage here will be T r into V 2. Now, writing the circuit equation for this, we have T s into V 1, that is, if we go here, T s into V 1 will be equal to T r into V 2 plus the drop which takes place here. If the current flowing in this line is I, then it will be I into Z, Z is equal to R plus j x. Therefore, we have T s into V 1 is equal to T r V 2 plus I into Z. Now, this will be approximately equal to T r into V 2 plus I into Z is I into R plus j x, which we can write as approximately equal to I into R cos theta plus I into x sin theta. Now, we also know that I cos theta will be equal to P by T r into V 2, because T r into V 2 is the voltage. So, V I cos theta is equal to the real power P. Therefore, I cos theta is equal to P by T r into V 2, and similarly, we have the reactive power Q is equal to T r into V 2 into I sin theta. This is the voltage into I sin theta is equal to Q. So, I sin theta is equal to Q by T r into V 2. Therefore, substituting these, we will get T s into V 1 is equal to T r V 2 plus this is R into I cos theta. So, R into I cos theta we are replacing by P by T r V 2. So, R into P by T r V 2 plus I x into I sin theta. So, x into Q by T r V 2, this is I sin theta we have substituted here. Normally, what we do is we want to keep T s into T r as equal to 1, because this is what will make the voltages proper on both sides. So, the product T s T r is generally kept as 1. Then if we do that, then we can write T r is equal to 1 by T s, and therefore, substituting that we get T s is equal to 1 by V 1, that is V 1 T s is equal to V 2 by here T r into V 2. So, T r into V 2 I am writing T r as 1 by T s. So, this becomes V 2 by T s plus T s into R P plus x q by V 2, which if we multiply the both sides by T s, then we get T s square is equal to V 2 by V 1, because this T s will cancel out, plus T s square because it is multiplied by T s. So, T s square R P plus x q divided by V 2. I am sorry, this should be V 1 V 2, and therefore, if we take this thing on this side, then we will get T s square 1 minus R p plus x q divided by V 1 V 2, because this here is V 1 V 2. So, 1 minus R p plus x q V 1 divided by V 1 V 2 is equal to this term V 2 by V 1. So, from this we can find out the value of T s for a complete compensation, that is when V 1 is equal to V 2. Mind it, we are writing all these values V 1 V 2 as per unit values. So, if we want both of them to be 1 per unit, then we can write this as V 1 is equal to V 2, or both side voltages becoming equal in this case here and here, both the voltages on the transmission line two ends being equal, that is the line is fully compensated, then V 1 is equal to V 2 and T s can be found out from this relationship from here, because V 2 by V 1 will be equal to 1, and solving this we will get the value of T s. Once we get T s, we know T r is equal to 1 by T s. So, we can also solve for T r. In fact, for any ratio of V 1 V 2, we can solve this for T s and then T r. Now, sometimes we would like to use a combination of the transformer taps as well as the reactive power injection devices, such as static VAR systems or static compensation, any static compensation device like maybe STATCOM and other devices. So, here I am showing this, there is between these two buses voltage V 1 is at the sending end and voltage V 2 is at the receiving end. We have a transmission line and maybe a 3 winding transformer which is connected near the receiving end, and the tertiary of the transformer we connect the static VAR system or static compensation device. The primary side we have this transmission line connected to the sending end, and secondary side we have the load connected, that is it is the receiving end bus. The whole diagram in electrical circuit can be represented by this, where we have V 1 the sending end, the current I is flowing through this, X 1 is the reactance of the transmission line, we have neglected the resistance. So, it is the reactance of the transmission line plus the reactance of the primary side of the transformer winding. X 2 is the reactance of the secondary side of the transformer winding, and X 3 is the reactance of the tertiary winding. And we have this as the transformation ratio, the transformer is shown here. Here we have the transformation ratio and we have a variable tap, that is T 1 2 is showing a variable tap between primary and secondary. So, by changing this T 1 2 we are basically changing the tap on the secondary side of this. Similarly, we have here on the tertiary we have connected the static VAR system or the STATCOM, which is a static compensation device. Normally, all these compensating devices we connect to the tertiary, and also it is always connected to the low voltage side for a simple reason, because developing or making these devices with low voltage is much cheaper compared to making these devices for very high voltage system. So, therefore, we normally connect these devices at the low voltage end. So, this is connected on the tertiary. Now, if you see, if P plus j q is the power which is coming from the sending end, we will have at the receiving end the power P r plus j q r, and if we want that the voltage of the system to be maintained, then what we need is to transfer less amount of reactive power from here. Less amount of reactive power from here, because we know that if we transfer less amount of reactive power, the voltage at this point will be much higher or much nearer to the voltage here, and therefore, by trying to inject the amount of reactive power through this compensating device, we can reduce or make this reactive power flow on the line and in the primary of the transformer to very low value or even 0. Sometimes we can even make it leading, and thereby we can control the voltage here. The other option is by changing the transformer taps, we can again regulate the voltage at V2. So, a combination of these two will give me a much larger variation over a larger load variation in the system. Now, many times we use regulating transformers. Basically, these transformers are used for injecting voltage into the transmission system. If we inject the voltage in the same phase as the voltage on the transmission system, then what we will be doing is either we can add the voltage and therefore boost the voltage, or if we want, we can inject the voltage in opposite phase, then we will be reducing the voltage or bucking the voltage. So, we can have a buck transformer or a boost transformer. Normally, in power system we will be using boost transformers most of the time, because with the increase in load, it is always the voltage which drops down. So, we try to inject voltage in phase with the voltage on the transmission line. That by that way we can control or the magnitude of the voltage. If we inject the voltage in not in phase with the transmission line voltage, but in quadrature or at some different angle, then we can be making a phase shift of the voltage as well, because the final voltage which is coming at the receiving end will be the sum of these two voltages, the sending end voltage plus the voltage which we are adding by this transformer. And since these two are phasors and they are not in same phase, we will get the resultant voltage having some phase difference from the voltage at the sending end or at the primary side of these transformers. So, here this is voltage magnitude controller or regulating transformer which controls the voltage magnitude only. If you look at this, here we have this transformer winding, which is a 3-phase winding connected to the 3-phase transformer, and we have taps on this winding. Now, based on all these 3 taps on the 3 phases are all ganged. So, they will move together. So, what we get is this voltage, whatever voltage we want here between these 2 points, will get injected here. So, this voltage can be added to the transmission line voltage in the same phase. Here this voltage is in the same phase as this voltage, and therefore, the voltage here is going to be the voltage at this point plus this voltage that we have added, because it is in phase. The same thing happens in all the 3 phases, and therefore, the secondary voltage gets increased by the amount of the voltage that we have injected. This is the way how we use the regulating transformer for increasing the magnitude of the voltage at the secondary of this regulating transformer. Now, the same thing if we do by injecting voltage which is not in phase, but in quadrature. If you look at this transformer, we have a transformer here like this, which is connected to the primary 3 phases AN, BN and CN are connected at these points. We have another winding which has half on this side and half on this side, that is the midpoint is connected to this point A, and this winding is having the phase of BC. Similarly, we have a winding here which is connected at the midpoint to B, and this has a phase which is same as AC. Similarly, we have another winding which is connected at the midpoint to phase C, and this has a phase which is same as AB. In this way, what we do is, if you look at the phase A voltage will be like this. Phase A voltage will be like this, phase B voltage will be like this, and phase C voltage will be like this. And therefore, we are seeing that we are adding or subtracting the voltage or adding any voltage which is in quadrature with phase A in this side or in this side. So, if we see in this present position, the 3 taps are placed like this, then we have a voltage V A on which we have this much voltage added, that is delta V A N is added here. Similarly, we have voltage B plus delta B N is added here, we have voltage C plus delta C N is added here, and if we see the phasor, it comes out to be V A is the voltage plus delta V A N is added here, V B is the voltage plus delta V B N is added here, V C is the voltage and delta C N is added here. So, now the new voltage A dash, B dash and C dash will be these points, and we see that though there may not be large change in the magnitude, the angle of these phases have changed, that is A dash is now leading A by this angle theta. Similarly, C is leading this C by this angle theta, and B is leading this B dash is leading B by this angle theta. So, this is what we call as a phase regulating transformer or phase shifting transformer. This is how it works, and we can change the phase angle of the voltage. And what is the consequence of changing this phase angle? As we have seen earlier, the real power P is given by V s V r by x into sin delta. Since V s V r are regulated to be very near to 1 per unit and x of the transmission line is a constant. Therefore, to change the real power flow on the transmission line, the only thing that we can do is change this angle, power angle delta, which is the angle by which V s leads V r. And therefore, if you see here, by changing this angle, we can change the power flow. So, by changing the angle of at V r or at V s, we can change the power flow on a transmission line, and phase shifting transformers are used for this purpose. Of course, nowadays with power electronic devices coming into picture, we have new kinds of controllers which we use for power system, transmission line voltage and power control. These devices are called flexible AC transmission system devices or FATS devices, because they allow you the flexibility of controlling the power flow and the voltage, and thereby the reactive power flow on the transmission line. So, both real and reactive power flow on a transmission line can be controlled using these FATS devices. Now, we will take up some simple examples on transmission line operation to understand the concepts that we learned in lesson 9 and 10. So, first example is a 50 hertz 132 kV 138 kV 3 phase transmission line is 200 kilometer long. The distributed line parameters are R is equal to 0.1 ohm per kilometer, L, that is the inductance, is equal to 1.2 millihenry per kilometer. The capacitance C is 0.01 microfarad per kilometer. The conductance is 0. The transmission line delivers 40 megawatt at 132 kV with 0.95 power factor lagging. Find the sending end voltage and current and also the transmission line efficiency. So, what we are given is the transmission line parameters, its resistance, its inductance and capacitance per kilometer length, and we have the line length given. We also know that the transmission line has to deliver 40 megawatt at 132 kV, means the receiving end voltage is 132 kV and the receiving end power is 40 megawatt at 0.95 power factor lagging. We have to find the sending end voltage, that is Vs, and current, that is Is, and also the transmission line efficiency. So, let us see how we work it out. Now, for the given values of R, L and C, we have omega, that is the equal to twice pi into f, f is 50 hertz. Therefore, we can calculate the series impedance per unit length or per kilometer as 0.1, which is the resistance, plus j 0.377, that is twice pi f into L, that is 1.2 millihenry per kilometer. So, this comes out to be 0.1 plus j 0.377, which is equal to 0.39 with an angle of 75.14 in ohms per kilometer. Similarly, the shunt admittance can be computed as j omega c, which comes out to be twice pi into 50 into 0.01 microfarad per kilometer. So, when we do that multiplication, this is j omega into c, then this comes out to be j 3.14 into 10 to the power minus 6. This is equal to 3.14 into 10 to the power minus 6 with an angle of 90 degrees. The unit will be mho per kilometer. Now, using this z and y, we can calculate the characteristic impedance ZC. ZC is given by square root of z by y. So, substituting the value of z and y, we get ZC is equal to 352.42 with an angle of minus 7.43. This will have units of ohm, because the length kilometer per kilometer will cancel out and this will have the unit ohm. Similarly, we can calculate gamma L. This is L is 200 and gamma is given by root z into y. So, substituting the values, we get this as equal to 0.2213 with an angle of 82.57 degrees, which can be written in rectangular coordinates as 0.0286 plus j 0.2194. So, now that we have calculated gamma L and ZC, we can find out also the values of sin hyperbolic gamma L and cos hyperbolic gamma L. Sin hyperbolic gamma L is equal to e to the power gamma L minus e to the power minus gamma L divided by 2, which is, after substituting the value of gamma L, will come out to be 0.2195 with an angle 82.67. Similarly, cos hyperbolic gamma L will be equal to e to the power gamma L plus e to the power minus gamma L, this whole divided by 2, which will come out to be, on substituting the values of gamma L this comes out to be 0.975 with an angle 0.37 degrees. So, knowing sin hyperbolic gamma L, cos hyperbolic gamma L and Z c, we can calculate the ABCD parameters for the transmission line. Now, the value of power and voltage specified in the problem refers to 3-phase and line to line quantities. That is, the values that we are given in the problem is in terms of 132 kV, which is a line to line voltage, and 40 megawatt, which is a 3-phase power. Therefore, the V2 or the receiving end voltage magnitude is equal to 132 by root 3. We are talking of per phase value or phase to neutral value. So, it is 132 divided by root 3, which comes out to be 76.2 kV, because we would like to work on a single phase basis. Therefore, we will convert all the line to line voltages into line to neutral voltages and 3-phase power into single phase power, that is power per phase. Also, we will use V2, the receiving end voltage, as a reference. Therefore, the angle of V2 we will take as 0 degree. Therefore, the phasor V2 is equal to 76.2 angle 0 degree in kilovolts, and the per phase power supplied to the load will be equal to 40 is the 3-phase power. So, 40 divided by 3, that is 13.33 megawatt. Given the value of power factor, which is 0.95, we can find out the current at the receiving end I 2. Now, we know P is equal to V I cos phi. So, the receiving end power P load will be equal to, this is cos phi, 0.95 into V into I, and therefore, substituting the value of P load and V 2, we get I 2 as equal to 184.1 amperes. We also know that the phase angle between V 2 and I 2 is given by cos inverse 0.95, which is the power factor angle. So, also since I 2 lags V 2 by cos inverse 0.95, which is 18.195 degrees. Therefore, we can write the phasor I 2 as I 2 is equal to 184.1 with an angle of minus 18.195, because I 2 is going to lag the voltage V 2, because the power factor is 0.95 lagging. Therefore, now we can calculate the sending end voltage V 1, which will be given by A V 2 plus B I 2, and A is cos hyperbolic gamma L and B is Z c sin hyperbolic gamma L. Therefore, V 1 is equal to V 2 cos hyperbolic gamma L plus I 2 into Z c sin hyperbolic gamma L. Now, if we substitute the value of cos hyperbolic gamma L, sin hyperbolic gamma L and Z c, then we will get the value of V 1 as equal to 82.96 with an angle 8.6 degrees in kilovolts. So, V 1 is 82.96 kilovolts with an angle of 8.6 degrees. Now, this is a line to neutral voltage at the sending end. Similarly, we can calculate the sending end current I 1, which will be equal to which will be equal to C V 2 plus D I 2. D is equal to A, which is equal to cos hyperbolic gamma L, and C is sin hyperbolic gamma L by Z c. Therefore, I 1 is equal to I 2 cos hyperbolic gamma L plus V 2 by Z c sin hyperbolic gamma L. Substituting the value of V 2 Z c sin hyperbolic gamma L, cos hyperbolic gamma L and I 2, we will get I 1 as equal to 179.46 with an angle of 17.79 degrees. Now, we can calculate the efficiency of the transmission. So, per phase input power will be given by real part of V 1 I 1 conjugate. If we do this multiplication, because we know V 1 is this and I 1 is this, we will take a conjugate, which means we will put a negative sign to this angle and then we multiply these two, then we are going to get, and we take only the real part of that, then we get this as equal to 14.69 megawatt. Now, per phase power which is received is 40 by 3, which is 13.33. Therefore, efficiency of transmission is output divided by input, which comes out to be 13.33 divided by 14.69, that is 0.907, or the efficiency is 90.7%. So, this is one simple problem that we solved. Now, we will take up another problem. Now, this problem states a 3-phase 132 kV overhead line delivers 60 MVA. Mind it, this is 60 MVA, not megawatt. 60 MVA at 132 kV and power factor 0.8 lagging at its receiving end. That is, VR or V2 is given as 132 kV and the SR is, the MVA value is given as 60 MVA at 0.8 power factor lagging. The constants of the line are given as A is equal to 0.98 with an angle 3 degrees and B is equal to 100 with an angle 75 degrees ohms per phase. Now, we need to find for this system sending end voltage and power angle. B, sending end active and reactive power. C, the line losses and wars absorbed by the line. Also, we would like to find out the capacity of static compensation equipment at the receiving end to reduce the sending end voltage to 145 kV for the same load conditions. That is, whatever voltage we have found out in A will be somewhat higher, and if we want to reduce this voltage by keeping the receiving end voltage is kept at 132, and now we want to keep the sending end voltage also at 145 only. That is, we do not want the voltage at the sending end to go beyond 145 kV, and therefore, we will require some compensation, reactive power compensation at the receiving end. So, we need to find out what is the rating of the compensating equipment for such a condition. Also, we need to find the unity power factor load which can be supplied at the receiving end with 132 kV as the line voltage at both the ends. Now, if we want to keep the voltage at both the ends at 132 kV, then what is the amount of unity power factor load, that is purely resistive load, which can be supplied by this transmission line. When we are working with 3-phase system, especially when we are calculating voltages and current, it is always better to work with the phase to neutral voltages and the currents flowing in each phase. So, what we do is, first we calculate the phase voltage. Now, for the receiving end, we have been given the voltage as 132 kV line to line. So, we divide it by root 3 to get the phase voltage, which comes out to be 76,210 volts, that is 76.21 kV, and we are choosing this receiving end voltage as a reference voltage. So, we fix its angle as 0 degree. Now, next what we have to do is, we need to find out the current at the receiving end. We know that the power at the receiving end is given as 60 MVA at a power factor of 0.8 power lagging. So, what we do is 60 into 10 to the power 6 gives us the 60 MVA, we divide it by the phase voltage. So, root 3 into the line voltage. So, this is 3 into 0.5, 3 to the power 0.5, that is root 3, into the line voltage, which is 132 kV, and the angle is given as cos inverse 0.8 with a minus sign to take care of the lagging power factor. When we do this mathematics, we will get the receiving end current as 262.43 amperes with an angle of minus 36.87 degrees. Next is we need to calculate the sending end voltage. Vs we know is equal to A into Vr plus B into IR, since we have already calculated Vr as shown here and IR as shown here. So, we substitute these values. So, A is given as 0.98 angle 3 degrees, Vr is 76,210 volts, plus B is given as 100 angle 75 degrees, and IR is given as 262.43 with an angle of minus 36.87 degrees. Now, here we have not taken any angle here, because the angle of Vr is 0 degree, which is the reference angle with respect to which we are calculating all angles. So, when we do this calculation, we find this as 74,685.8 with an angle of 3 degrees plus 26,243 with an angle of 38.13 degrees. And finally, when we calculate this, we get this out as 74.59 plus j 3.909, which we are, this polar coordinate value is converted into rectangular coordinate values, and this polar coordinate values is put into rectangular coordinate values, then it comes out to be 20.64 plus j 16.20, and since these are in thousands, so we are multiplying this into 10 to the power 3. So, here instead of writing these thousands, we have taken this 1000 here. So, when we do this calculation, this comes out to be 95.23 plus j 20.11 into 10 to the power 3, that is equal to 97.33 into 10 to the power 3 volts with an angle of 11.92, which tells us that the sending end voltage, phase to neutral voltage, is 97.33 kV and the power angle is 11.92 volts, because this is the angle of the sending end with respect to the reference. If we want to find out the line to line voltage at the sending end, then we multiply this by root 3. So, when we do this, we get this as 168.58 kV, and the power angle, as we have seen, is equal to 11.92 degrees. Now, for the B part, where we need to find out the sending end real and reactive power, we have 3 phase power in megawatt given as SS is equal to A Vs square divided by B with an angle of beta minus alpha. For division by B, we are writing B inverse, that is 1 by B, minus Vr Vs divided by B with an angle beta plus delta. Now, here mind it, when we are writing this as 3 phase power, then we are writing Vs Vr all as line to line voltages. Therefore, substituting the values, we have A is 0.98, Vs is 168.58. So, into 168.58 square divided by B, which is 100 at an angle of beta is 75 and alpha is 3 degrees, minus Vr into Vs, that is 132 into 168.58 divided by 100, which is B in here. So, with an angle of beta plus delta, that is 75 degrees is beta plus delta is 11.92, as we have calculated in the previous part. So, putting all these values and solving, we have got this SS is equal to 278.49 at an angle of 72 degrees minus 222.53 at an angle of 86.92. We do this calculation for calculating the real part, what we need to do is take the cos of these angles, and for reactive power we take the sine of these angles. So, P s is equal to 278.49 cos 72 minus 222.53 cos 86.92, which comes out to be 86.06 minus 11.696, that is the sending end real power is 74.10 megawatt. Now, since we have used these kilovolt values here, the power will be in megawatt, because multiplication of 10 to the power 3 and 10 to the power 3 will give me 10 to the power 6. So, the power here is directly in megawatt when we are using the voltages as kilovolts, and if we are using line to line voltages, then the power is a 3 phase power. So, this is a 3 phase power. Sending end power is equal to 74.10 megawatt. Similarly, we can calculate the sending end reactive power Q s, which will be 278.49 into sine of 72 degrees minus 222.53 into sine of 86.92 degrees. That is, we have to take the sine of the angles what we had got for S s. Therefore, this comes out to be 264.89 minus 222.21, which is equal to 42.65 megawatts lagging. So, this way we have calculated the sending end real and reactive power. Now, in part C we need to calculate the line losses and the megawatt absorbed by the line. So, line losses will be nothing but whatever sending end power is there and whatever power is received. If we take the difference of the two, that much amount of real power is lost in the line or lost in the resistance of the line or dissipated by the resistance of the line. Therefore, line losses is equal to P s minus P r, which is equal to 74.10 minus the receiving end real power will be 60 into 0.8. So, MVA into cos phi. So, 60 into 0.8, that is 48. So, therefore, line losses comes out to be 26.10 megawatt, which is quite a large amount of loss. Almost 1/3 power is getting lost in the line. Similarly, MVAR absorbed by the line will be whatever is the MVAR at the sending end, whatever is being sent on the line, and whatever is being received at the receiving end. So, Q s minus Q r, which is coming out to be 42.65 minus 60 into 0.6, that is sine of the power factor angle. So, this is 60 into 0.6, which comes out to be 6.65 MVAR. That is, this much 6.65 MVAR is being absorbed by the line itself. Next, we say that we want to keep the sending end voltage at 145 kV and the receiving end voltage is kept at 132 kV, then what is the amount of compensation that is required? Now, since we are transmitting 60 MVA at 0.8 power factor lagging, which comes out to be 48 megawatt. Therefore, for this P r is equal to 48, V s is equal to 145 kV, V r is equal to 132 kV. Since this is in megawatt and these are in kV, so we need not write those 10 to the power 3 and 10 to the power 6. So, P r is equal to V s V r divided by B into cos beta minus delta minus A into V r square by B into cos beta minus alpha. Now, here we know P r value is 48. So, we substituting all the values, we will get 48 is equal to 145 into 132 V s into V r divided by 100 into cos of beta minus delta. Now, here we do not know, we know beta, but we do not know delta for this particular operating condition. Therefore, we have not substituted any value here, and for these terms A is 0.98, V r is 132. So, A V r square divided by B into cos beta minus alpha, that is 75 minus 3. Now, from this again if we solve this, we will get cos beta minus delta is equal to 0.5275, or angle beta minus delta is equal to 58.16 degrees. Now, we know beta as 75. So, we can calculate delta very easily, but we do not need the delta value as such. What we need is angle beta minus delta. So, we will use this. Now, we know q r is equal to V s V r divided by b into sin beta minus delta minus a V r square divided by b into sin beta minus alpha. So, again substituting the values, we will get q r is equal to 145 into 132 divided by 100 into sin 58.16, this is beta minus delta, into a 0.98 into V r square 132 square divided by 100 into sin 72 degrees. So, after calculating, this comes out to 162.60 minus 162.40, which is equal to 0.2 megavar. Thus, for a V s of 145 kV, V r and V r of 132 kV with P r 48 megawatt, a lagging megavar of 0.2 will be supplied from the line along with the real power of 48 megawatt. Now, since the load requires 60 into 0.6, that is 36 megawars lagging, the static compensation equipment must supply the rest, because the line will supply only 0.2 megawatt. So, the static equipment must deliver 36 minus 0.2, that is 35.8 megawatt lagging, or it must, or we can say it must absorb 35.8 megawatt leading. That means, the static compensation there has to be capacitive to provide this much megawatt. The capacity of static capacitor is therefore 35.8 megawatt. The third part was, if we keep both V s and V r equal to 132 kV and the load is unity power factor, that is q r is equal to 0, then what will be the power that we can supply. So, using this identity q r is equal to 0, we will write q r relationship as q r is equal to V s V r by b into sin beta minus delta minus a V r square by b into sin beta minus alpha, and substituting all the values here, we can calculate the angle beta minus delta, which comes out to be 68.75 degrees. Now, since we have calculated beta minus delta, we can write down the equation for P r, V s V r by b into cos beta minus delta minus a V r square by b into cos beta minus alpha. Now, substituting all the values, we will get this as 10.36 megawatt. That is, if we want to keep the voltage at both ends equal to 132 kV and we want to supply a unity power factor load, then the load that we can supply will be only 10.36 megawatt. Now, let us take another example. A 220 kV line has tap changing transformers at both ends. The transformers at the sending end has nominal ratio of 11 to 220 kV, and at the receiving end 220 to 11 kV. So, step up transformer at the sending end, step down transformer at the receiving end. The line impedance is 10 plus j 40. Again, we are using a short line model. So, 10 plus j 40 ohms, and the load at the receiving end is 100 megawatt at 0.9 power factor lagging. Assuming that the product of off nominal tap settings is 1, that is T s into T r is equal to 1, as we said earlier, find the tap settings to give 11 kV at load bus. Okay. So, this is the example for what we did for tap changing transformer in today's class. So, now S is equal to 100 MVA, that is 100 megawatt is being transmitted at 0.9 power factor lagging. So, S per phase will be 100 into 10 to the power 6, this is megawatt, divided by 3. So, that is megawatt per phase divided by 0.9 will give me, because 0.9 is the power factor, this will give me the MVA. So, this is megawatt divided by the power factor gives me the MVA. So, this comes out to be 37.03 into 10 to the power 6 volt ampere, or 37.06 MVA per phase, and P is known as 100 megawatt. So, per phase is 33.33 megawatt. Therefore, we can calculate what is the value of Q. Q will be S square minus P square, square root of that. So, this comes out to be 16.16 megawatt per phase. Now, we have V 1 is equal to V 2 is equal to 220 kV, and since we want to work out on a per phase basis, so we divide it by root 3. So, we will get the line to neutral voltage. So, 220 into 10 to the power 3 divided by root 3 volts, this is coming out to be 127.02 kilovolts. Now, R is given as 10, X is given as 40. Therefore, substituting this on the relationship for the transformer that we had derived today, 1 by T s square is equal to 1 minus R into P plus X into Q divided by V 1 V 2. So, substituting all these values of R, P, X, Q, V 1, V 2, we get T s is equal to 1.0317, and therefore, T r is equal to 1 by T s, which will be 0.9692. So, if we keep these off nominal taps, T s as 1.0317 and T r is equal to 0.9692, both end voltages will be equal to 220 kV line to line. So, with these 3 examples, we will end today's lesson, and in the next lesson we will review whatever we have learned about the transmission line. So, thank you very much. Welcome to lesson 11 on power system analysis. In this lesson, we will be mainly reviewing whatever we have learnt on transmission lines. That is, basically we will be again going through the whole set of lessons that we did, that is from lesson 3 to lesson 10, and we will try to recapitulate whatever we have learnt in those lessons. In this lesson, we will start with introduction to transmission systems. So, with this we stop today, and we will continue with this review in the next lesson. Thank you.